Okay, welcome back to Real Analysis. Last time, if you recall, what did we talk about last time? Metric spaces, good. We began discussing this concept of how you put a notion of distance on a space of things, right? And so a metric space is really a set together with a notion of distance, okay? Today what I want to focus on is a very, very important concept. It's the concept of a limit point, and we defined that last time, but let me just remind ourselves what we did. So we have the idea of a metric space. So a metric space is really, this is just a set together with a metric, which is a notion of distance. And the metric satisfies three properties. Who remembers what those three properties are? Non-negativity, and it's going to be 0 if and only if the 2 points are the same. So the distance between 2 points will only be 0 if the 2 points are the same. Okay. What were the other two properties? Good. Non-negativity, symmetry, distance between P and Q is the same as distance from Q to P, and the triangle inequality. Okay? And that is often the most interesting one to check if you want to verify that something is a metric. Okay, so we've seen some of the usual metric. Usually when you say Rn, what you really mean is Rn together with the Euclidean metric. And this Euclidean metric is really what you normally think of as the usual metric. If you don't specify it, you just assume that Rn has the Euclidean metric. And that's given by the absolute value of the difference if it's a real number. And in higher dimensions, it's the square root of the sum of the squares of the differences of the two vectors. Okay? But there are lots of other metrics. We saw some last time. The staircase metric, which basically said instead of square rooting the sum of the squares of the differences, what did you do instead for the staircase metric? Yeah, take the sum of the absolute values of the differences between the coordinates. So that basically measures how far it would take to walk from point A to point B if you only used north-south or east-west motion, right? Okay, that's a notion of distance. We saw some other examples last time also on other spaces, like on the space of genome sequences. You might have a distance that just measures the number of places that the two genome sequences differ. Okay, lots of sets you might be interested in, and we'll see many examples of this going forward. But of course, the most concrete example that you're familiar with is Rn. There are some exotic metrics. I don't think we mentioned this last time, but here's one which might have you think about. Let's endow Rn with the discrete metric. Actually, this can be done with any space X. It doesn't even have to be Rn. It could be X, any space, any set X. And the discrete metric is it's a very curious metric. Let's see. Let me give it a name that looks different from other things. I'll just make this up. How about delta? Delta. Okay. What's a discrete metric? Well, it basically says let's take the difference. Let's take the distance between P and Q to be either 0 or 1. It'll be 0 if P equals Q, and it'll be 1 otherwise. Let's see. Is that a metric? Dhruv is nodding his head. Why is it a metric? Good. The most interesting one being the triangle inequality. Why does this satisfy the triangle inequality? Good. In the triangle inequality, the left-hand side is 1, and the right-hand side is either 1 or 2 if these points are different. Okay, so again, easy to check. Okay, so what is the discrete metric doing, morally speaking? It's basically saying what, Willie? Are they the same point or not? And if they're not, we think of them as distance one from each other. Okay? So imagine the real line with the discrete metric. That's basically just a cloud of points that are all, you consider them distance one, right? So somehow this idea of a metric begins to create a geometry, right? Which is different from the usual geometry of the real line, right? The real line with the Euclidean metric looks like this, right? But the real line with the discrete metric looks like a cloud of points, right? An uncountable cloud of points, and those points are all distance one from each other. Yes? You might say, well, how is that possible? Well, it's not sitting in any space, right? We are telling you what the distance is, right? Okay. Okay. Good. So that's what a metric was, and the associated notion, of course, here is once you have a metric, is you can start talking about which points are close, and one way to gather close points together is to talk about neighborhoods or open balls. So these are the open balls. That's one way to say it. Another way to say it is a neighborhood. I'll talk about a single open ball, or a neighborhood. I'm abbreviating, so I don't have to write out neighborhood. Is basically a set that basically looks like a ball around a point, right? So sometimes we'll write like this, n sub r of x. It's basically, here's x, here's a ball of radius r, and the neighborhood is this ball. It's all the points inside. Okay? You could write that out. We did that last time, wrote out the set. It's a set of all x such that set of all y such that the distance from y to x is strictly less than r. Okay, that's why we call it an open ball. It doesn't include r. If I included distance r points, that's all the points on the boundary, then this would be a what? We call it a closed ball. Okay? But the open ball or the neighborhoods are the things that will be of interest to us. So these are, in some sense, the points that are close together. So they tell us which points are close. Now, if you want to be really explicit, you could tell me what the distance is. But if you just gather things that are similar distances, that's sort of what the idea of a ball is. And when you take topology, you'll be basically redoing analysis, just referring to open balls and ignoring or not working, not referring to a metric. Willie?
So if you take the metric to be a discrete metric,
Mm-hmm.
and you have no ball, you say the radius is less than 1.
Yes.
Is that sort of almost a closed ball? Because there's only, it's just 1 point.
Excellent question. Willie's question was, what are the open balls for a space endowed with a discrete metric? That's a great question. So you take x with a discrete metric. So in x with a discrete metric, the open balls are, tell me what they are. Just use the definition. It could be 1 point or it could be all the points. That is, it'll be all the points if the radius of the ball is distance 1 or bigger. Happy with that? Thank you. Bigger than 1. And if it's 1 or smaller, thank you, then the ball is going to be just points. That's correct. Are single points if r is less than or equal to 1. Thank you. And or everything, or all of x if r is bigger than 1. Okay, so now Willie was asking, well, what would the notion of a closed ball be? What are the closed balls if r is if r is, let's say, a half, the open ball is just a single point x. The closed ball is just a single point x. That's correct. So they are the same thing in this weird space. Okay? It's not so weird, actually, because the discrete metric is really, it's a very natural metric. Just tell me if two things are different. Okay? This is the metric that perhaps be most useful to a computer scientist. Tell me if two things are different. Okay. Great. So we have this notion of balls, and now we can define what it means to be a limit point. Now, of course, the motivation here is to give me some sense of when a certain set of points is getting close to another set of points, right? So the question we might ask is, when does a set, let's say E, if you like, approach, in quotes here, because I haven't defined this, I'm just saying, approach a point X. That's sort of the question, right? Or point P. Let's use the letter P. Okay? So, you might have a couple of different pictures in your head. One picture might look like this. Give me a bunch of points like this, right? And then there's like, these things seem to be approaching this point, P. And these might be some points in the set E. But it doesn't have to look as discrete as this, right? It could look like this. It might be that, you have just basically a set like this. And you have a point P right on the boundary, right? Or a point P inside, right? I mean, certainly, if you're inside this set, you can find a bunch of points that somehow approach this one point P. With me? So how would we, being mathematicians, how would we define a concept that would capture this idea? And that's the concept of a limit point. Okay, so here's the definition we ended last time with. So if you have a point, let's say P, in some big metric space X, from now on, all spaces will be metric spaces, unless I otherwise say. Okay? You have a point P in some space X, we'll say is a limit point of a set E if every neighborhood, did I say some neighborhood? No. I said every neighborhood of P contains a point Q in E, where Q is not the original point P. Okay? So in other words, it contains some other point Q that isn't P. Hugely important definition. It has to be true for every neighborhood of P. That is, every ball around P. Okay? So let me do a couple examples here, and these will actually be our running examples. In fact, since I'm going to use these examples a lot, I'm just going to put them on this board here. In your notes, you could still put it there, but I'm going to put it to the side here because we'll work on this board quite a bit. So here's one example in R. Suppose I have the set G, which is a set of all 1 over n, such that n is in Z. N is in, let's say, the natural numbers n. Take a look at that set. An example, this picture would look something like this. Let's mark it with a bunch of points here. Here's 1, and this is 0. And this is the set of all reciprocals, isn't it? A half, a third, a quarter, a fifth, etc. Okay? Everybody happy with this picture? Okay, So here's a question for you. For this example, are there any limit points of this set G, which is the green points? Yes? Where? 0 is a limit point. Excellent. Let's mark it here. The claim is 0 is a limit point. Okay. Why would 0 be a limit point? What's the justification? Well, it better be true that every ball around 0 contains a green point. Is that true? What's a ball look like in R? Good. A neighborhood, so let's just mention that. Notice that neighborhoods of P look like P minus epsilon, P plus epsilon for some epsilon. So they're like some interval around P of some radius, right? So in this picture, what do we have? Here is one such ball. It looks like this. Well, any such ball contain a green point? Yes. So 0 is a limit point. Very good. Oh, okay. Let's do another example. Here's another example. This is in R2. I'm going to describe a set B. Consider the set B. And I'm just going to draw this picture in the plane, if that's okay. So the picture, it doesn't even matter if I have axes here. I'm just going to draw. Here, forget the axes, because it just clutters up the picture. Here's what I'm going to do. Here's a set B, okay? How about this? So I'm going to be consistent here and make these green. The sets are green. There. There's a point here. There's a point here, okay? There is a set here, which kind of looks like a rectangle. And I'm dotting the top, which basically means don't include the points on the boundary here. And then I'm making these solid, which means include those points, okay? And I'm going to let the set be everything inside as well. Happy? Okay. Happy? Okay. And then let's give this thing, I don't know, let's add another little set here. How about this? Okay. And now let's include everything inside except for one little point that's missing, okay? So this is really hard to see, but there's a point I've taken out. So this is a disk not containing its boundary with a point missing. Okay, so there's a point missing. Okay? Everybody happy with that? Okay, so let me label some points here. Let's call this point A. Let's call the point missing out of the nose there B. It's like a little nostril, if you like. Let's call a point on the boundary here C, a point here D, and a point here E. And let's place some point outside this picture. Let's call this point Z. Okay, question. Which of these points, these labeled points, are limit points of the set B, which is the green points? Which points are limit points according to the definition? Take a second to discuss it with your neighbor. Which points are limit points? Okay, question. Is E a limit point? Everybody, I want everybody to answer. Yes, it is. Okay, because any open set, any ball, no matter what radius it is, no matter what size ball I draw around this, would you agree that it intersects a green point? Good. So E is a limit point. Is D a limit point? Is C a limit point? Yes. Notice the definition doesn't require P to be in E or not. It could be in E, doesn't have to be in E, right? Just requires that there's some other points, no matter what neighborhood you take, there's some other green points in that disk. With me? All right. Perfect. So C, D, and E, is A a limit point? Why not? It contains a point of E. That's A. Can't be the same point. So A is not a limit point. Is Z a limit point? Good. C, D, and E are limit points. Z and Z are, A and Z are not. Okay. This actually, excuse me. Oh, we didn't even talk about B. Yeah, question. Is B a limit point? Yes. Thank you. It's not in the set, but any disk will contain a point, a green point. Excellent. Okay. That being said, it's actually going to be helpful for us to maybe say when is a point not a limit point. And this learning to negate a condition or a definition is a useful skill. So I want to spend a few minutes talking about that. So if P is a limit point if all these things are true. What does it mean to say a point is not a limit point? So let's say a point P is not a limit point of E. What does that mean? Go ahead. Yeah, so Rebecca's saying, if there exists a neighborhood, N of P, such that what? I'll just say it this way, any other points of E. Everybody happy with that? Willie? Excellent. Can you hold that question for a second? I'll come back to that. The question was, if you have a limit point, does an open ball have to contain infinitely many points? We're going to answer that question in just a second, but if you're bored, you should try to think whether that's true. If it's true, come up with an argument. Excellent question. We're going to come back to that. Now, so does everybody see why this is the negation of this? That is, if I want to say something's not a limit point using this definition, what happened here? How did I get from this statement to this statement? What happened to every when I negated it? It turned into a there exists, and then what happened to the rest of it? For every blah, something is true. It became there exists a blah such that something is not true. Okay, so this is just a little bit of logic. So let me just put this here. In fact, if you don't mind, I'm going to put that here because it's sort of an aside. So I'm going to put it to the side. Okay, so just a little logic practice. We're going to see what it means to negate a statement. So let's define a horse. We'll say a horse is superior if every leg is strong. Okay, now I just made up this definition. It's not something that horse people normally use. Okay, I just made up this definition. Okay. Horse is superior if every leg is strong. So, a horse is not superior, not to be confused with supremum. Not superior. How would I negate this? Good. If there exists a leg that's not strong. Okay, so this is exactly the same thing that happened over there. This is just an example. So let's just point out what exactly happened here. Really, what we have here is a condition that looked like this. A horse is superior if, for all x, x being a leg, ax is true. Okay? And that turned into there exists a leg such that AX is false or not true. Happy with that? So when you negate, this is actually really helpful when our definitions start getting really complicated to remember this. Negation turns a for all into there exists. And then it changes it negates the statement following. Okay, what if I had a statement that was there exists and I negate it? It becomes a for all. Okay, so an example here might be a horse is lame if it has a broken leg. Right? Would you agree it just takes one broken leg to be lame? Yeah? Maybe? So, it's not lame if what? If every leg is not broken. And once again, what I want you to see is this becomes, there exists a leg x such that AX is true. It became for all x, AX is not true. Everybody happy with this? Bonnie? Not according to my definition. Right? I just made a definition here that said a horse is superior if I'm requiring every leg to be strong in my definition of superior. Okay? Was that your question? Yeah, I mean, oh, sorry, yes. So the question was, what is the meaning of this word if, right? Yeah, so this is an ambiguity that almost every math textbook does and doesn't deal with. When we make a definition, the if in this statement really means. Okay? We say a horse is superior. To say a horse is superior means every leg is strong. Okay? But this if is not the same as a conditional if that's an implication because it's a definition. Does that make sense? Yeah, that's an excellent point. This is not to be confused with an implication. And by using the term if and only if, you're only making people think it's somehow not a definition, right? It's a conditional. But you could, if you're happy, write if and only if. But what we really mean by this if is means. Yeah. Okay. So there are no other situations besides this that you'll call a horse superior. I think that was your question. Okay, that's true of all these. In all these places here. When we say if in a definition, we mean if and only if. We mean means. Okay, great. Okay, so that's a little aside for for logic. Let's. There's going to be a number of definitions we're going to make here because we're really learning some terminology related to what we call the topology of the real line. By the way, the topology is a word I'm not sure your book defines either, but it's in the chapter title. Topology just refers to the set of open balls. Okay, so a collection of open balls is called a topology. And it actually comes from, you'll see in the class topology, you basically do a lot of this stuff without a metric, and you just refer to open balls. Okay, great. Let's see. We looked at this example here, and we said A and Z are not limit points. So let's just check that it satisfies this statement. A point P is not a limit point if there is a neighborhood that doesn't intersect any green point. Is that true of A? Well, any other green point besides A itself, yes? And Z, is that true? Yes, look. So all you have to do, unlike the case of showing something is a limit point, to show something isn't a limit point, you just need to find one ball that misses points of E, all the points of E other than this point itself, possibly. Yes? Mary, you happy with that? Okay, and is that true here? I mean, I could find this big ball would contain points of V, but to say it's not a limit point just means you have to find some ball that doesn't. Okay? Happy with that definition, Paul? With that statement? Yes?
With open ball style treatment here, R is just a real number, or is it restricted by the allowed values of the metric?
A metric values are always real numbers.
Right, but for instance, in a space with a discrete metric, is every point a limit point, or is no point a limit point?
Ooh, excellent. I was just about to ask that. That's an example I want people to think about, right? But you should think of a metric as, so in the discrete metric, the possible, the distances that you get for any pair of points is 0, 1. But you can talk about a ball of radius 1/2. I think that's the question you're asking. And now you should try to answer that question. Is in a discrete space, is everything, what are the limit points? We'll do that example in a second. So is everybody happy here that this point is not a limit point because you can separate it by an open ball from the green? Now, I claim A and Z are slightly different in nature, in character. Even though they're not limit points, A is in the set, whereas Z isn't. Okay, so we have a special name for points that are in the set but not limit points. Because, for instance, D is in the set, but it is a limit point, isn't it? So what do you think we call points that are in the set but not limit points? It's not called interior. It's called isolated because it's all by itself. So I'm going to make a definition just to make sure that we have this stated explicitly. P is an isolated point, E, if this means what? P is in E, and P is not a limit point of E. Okay? Everybody happy with that? So, question. Are there any other isolated points in my face? The other eye. Anything else? Anything else? Form an opinion, please. Anything else? No, very good. What about the set G? Are there isolated points of G? Which ones? All of them? 1 is, I agree. 2 is? 3 is? 1/3 is? Okay. 1/1,000,000th is? Yes, because I can find a small enough neighborhood around it that misses 1/1,000,000th and 1 and 1 over 99,999,999. Yes? Right? Oh, okay, good. So all the green points are isolated points. 0 is not in the set, so it can't be isolated either. Correct? Okay, good. So example, so here's a definition. So the example here is all points of G are isolated. The eyes of B, about to say Texas, the eyes of B are isolated too. Okay? Great. Now, let's look at a point. Some of you said D is kind of very different than A. D happens to be a case where, what? How is D different from A? Well, yeah, D has the property that if you take a ball around it, that there is a ball around it that not just intersects G, the set B, but the whole neighborhood is inside, isn't it? Right? That's kind of like way on the opposite extreme of being isolated. Yes? So we have a special name for that. So this is hard to read. A special name for that is, we say that, I'll just do it here, definition. we say P is an interior point. Is that a good name? That's a pretty good name, yeah, for something that's so far inside that there's a ball that contains, that's completely contained in the set. So P is an interior point of E. What does that mean? If there exists a neighborhood N of P such that N is completely contained as a subset of E. I'm just going to box all these definitions because they're useful. Okay, let's see. Is that true of this point D? Is it interior? Are there any other interior points in this picture? Not labeled, but are there others? Yes, Mary, tell me where the other ones are. All these points are interior. What about the point on the boundary here? No, not interior. What about point right here? They're not even in the set. Okay, so they clearly can't be contained. Neighborhood can't be completely contained in the set. What about in here? Are there interior points here? Yeah, all these points. They're all interior, aren't they? Yes.
In our definition, do we need to add that P is in? Oh, you said that. P is in.
Yeah, we don't need to add it here because the neighborhood contains P, and we're requiring that N is completely contained in E. Okay. Excellent question. So it doesn't need to be in the definition. Great. Okay. Just a little bit of practice here. Help me negate the statement. P is, that's not my public service announcement, but it's a good thing to do. Okay. Help me negate this statement. P is an interior point of E. So what does it mean to not be, P is not an interior point means what? See, if you remember this, it'll be very easy to do this. If for every neighborhood of N, N is not completely contained in E. Now, this is an example where you might want to go a little further. What does it mean for N to not be completely contained in E? There exists a point in N that's not in E, right? Do you see that that is the negation of this statement? This is actually a for all statement, right? For every point of N, that point's in E. So we've just flipped there exists to a for all, and a for all to there exists. With me? Okay, using our little horse logic. All right. Excellent. Let's see. Are there any interior points of G? So, example, G has no interior points. Okay. D is an interior point of B. And there are others. That's the example. All right. So here's what I'd like you to do now. I'd like you to take a minute or two to decide to think about the following examples. So, example. Let's look at in R. I want you to look at these sets. So consider the set. Consider the empty set. Consider the whole set. Consider the rationals. And then I want you to do the same thing in R discrete. That is, R with discrete. Consider these same sets. And the question I want you to answer is, what are the limit points? I'm going to abbreviate limit points. What are the limit points? What are the interior points? What is the what are the other definitions we have? Isolated points. Now, notice that I'm asking you first to do it for R, and then think about the discrete metric. Okay. So take a couple of minutes. We'll take a couple-minute break, and you can stretch, and we'll try to answer these questions. Oh, before the break, let me see what your questions are. Yes, Dylan. From here on out, it's not a standard enough notation to do that. So if you do use it, you should remind the reader that's a discrete metric. Question? Yeah. Oh, excellent question. Is point B an interior point according to the definition? No, why not? Excellent, because B is in N, but B is not in E. B is in the neighborhood. So this is, in fact, a good example to put out here. B is not an interior point of big B. Excellent question. Okay, we'll take a couple-minute break, and during the break, you can think about these examples here. Okay, are we, I guess we're going to, let's resume. So let's think about these examples. There are 6 examples here. The empty set. That is a subset of the real line, isn't it? Does the empty set have any limit points? No. Well, let's see why not. Willie says no. Why not, Willie? Okay, so you're saying it has no limit points because to be a limit point, so you're claiming that no point of R is a limit point of the empty set. So maybe it's easier to use the negation here. Is it true for any point P, there is a neighborhood of P in the real line that completely misses the empty set? Yes, trivially. Okay. The other way to see it is, of course, to go back to the original definition and say, is it true that every neighborhood of P, whatever the P is, contains a point of the empty set that's different from P? No, because there's no points in the empty set. Okay, happy with that? So, empty set has no limit points in the usual metric. What about under the discrete metric? It still is the case that any point P has a neighborhood around it that completely misses the empty set, correct? Good. So the empty set has no limit points in either situation. What about the entire real line? Does it have limit points? Yes, every point is limit point. Very good. What about in the discrete metric? Under the discrete metric, remember the discrete metric is balls could be single points or the whole thing. Is it true? So are there limit points? If the subset is the entire real line, are there limit points? Can P be a limit? Let's draw a picture here. Here's R, and I'm looking at it as a subset of itself. And I want to know, does it have any limit points? And some of you claimed what? It has no limit points? You want to justify that? Give me a point P. Is it true that P is not a limit point? Well, to not be a limit point means there is a neighborhood that completely misses other points. Is there a neighborhood of P that completely misses other points under the discrete metric? Yes, because under the discrete metric, the balls are points and the whole thing. Okay, so notice that in our discrete, P has a neighborhood, namely just P, that completely misses, that does not contain other points of E, which is R in this case. So E, which we're letting be R, has no limit points in R, discrete. That's the claim we just made. Okay, everybody happy with that? Let's just think about it. We're not going to do all these examples, but let's think about another example. Does R as a subset of itself have any interior points if the metric is discrete? Yes. Now I see at least one person shaking their head no, and one shaking their head yes. So let's have a debate here. Patrick.
So it's an interior point if it has a neighborhood such that that entire neighborhood is contained in the set.
Okay.
Yeah, so let's choose some neighborhood around a point. Well, everything in that point is also, and everything in that neighborhood is also in R. Therefore, it's an interior point.
Okay, excellent. And I see Willie agreeing now. So at least two people believe that every point is an interior point. Is that the claim? Good. Yes. So in our discrete, every point in our discrete is an interior point. Does everybody agree with that? Okay. Interesting. That actually should maybe make some sense to us, because really I've drawn the picture in the wrong way. This isn't the geometry of R discrete. The geometry of R discrete is it's a cloud of points, all distance 1 from each other, yes? So what does it mean to have limit point? Could a cloud of discrete points have a limit point? Can things accumulate on any point? No, there's no points it can accumulate on, right? This is the wrong picture, right? The metric gives us a sense of what the geometry should look like. Is every point an interior point? Yeah, because you take a ball of radius 1/2, it completely contains just 1 point, and that's in the set. You happy? Right? So this is actually the wrong picture. This is really what the picture should look like. This is discrete space, isn't it? Right? I mean, it doesn't even quite look like this, because this makes it look like these 2 points are farther from these 2 points, but all the points are alike. And now this point P, definitely, it maybe is more obvious what it should look like. If you wanted to embed the discrete space in a Euclidean space, it would have to be infinite dimensional. In fact, it might even, if it's an uncountable set, it would have to be R to an uncountable product of R's, okay, which we could define. But what I want to get you away from is thinking of sets as necessarily being embedded in a Euclidean space, because Euclidean space is just one example of a space, right? Yeah, excellent question. Really, if you want to think about it, I mean, it's a simplex, right? It's corners of a big tetrahedron. That's what we're doing, right? If we're placing them all distance 1 from each other, it would just have to be infinite dimensionally tetrahedron if the set were infinite. Okay, excellent. Let's think about Q. What about Q? In the regular real line, does it have any limit points? The rationals, does it have limit points? Yes? Which points are limit points? Every point is a limit point. So E and Q in R. Claim has what as limit points? Every point? Why? Well, we haven't used the word dense yet, but why is every point a limit point? Now, in R, of course, the picture looks like this, doesn't it? Whatever. Get the picture. Okay. Now, these are all, so E is actually a subset, right? It's the green subset here is just these points, right? Okay. Now, what do you claim as limit points? You claim every point's a limit point. Is that true? Is it true that no matter which point P I take, a ball will contain rationals? Yes! We've proved that, right? Okay. So in fact, in R, E equals Q has all points limit points. Has all points of R as limit points. All points of R, in fact. Any real number is a limit point. Okay? It didn't matter where that point P is. Oh, interesting. Very good. Okay, so that's kind of neat. What about are there isolated points of Q? No. So similar. Well, easy way to see that is isolated point can't be a limit point, can it? Right? Everything's a limit point, can't be isolated. Excellent. What about the discrete metric? Explode the space and then take a subset of those that are rationals. Are there limit? No limit points, right? For the same reason that R had no limit points, right? This is a smaller set. Can't have limit points. Okay, excellent. So good practice there. Let's turn to a theorem that, a question that Willie asked, which I just gave away, so I'll just tell you the answer is yes. The question was, is it true that if P is a limit point of E, then, in fact, every neighborhood contains infinitely many points of P, contains not just one point, but infinitely many points of E? That was Willie's question. Is that true? Well, I claim it is. Can somebody give me an argument why? Katie? Oh, interesting. Okay, so let me draw a picture here, if you don't mind. Here's a set E. Here is P, which we claim is a limit point of E. Ooh, okay. Ooh, I like that. That's nice. Okay, great. So here's a proof by contradiction. Thank you, Katie. Proof by contradiction starts off by saying, okay, well, what's the negation of every neighborhood of P? There exists a neighborhood of P which doesn't do this, which doesn't contain infinitely many points, right? With me? So there exists, so by contradiction, I'm just sketching this. There exists a neighborhood N of P with only finally many points. Okay, good. And we might as well give these points of E names. How about calling them, E1 through En? There we go. Here's a neighborhood, and it has these points, E1 through, there are only finally many, En. And now Katie says what? There's going to be a least distance. Why is there going to be a least distance? Because every finite set of numbers has a most element, right? Or actually, it's really the has an infimum, right? Which is achieved. Okay, which you proved on your homework, right? You did the supremum version. So here we go. Consider. I'll just cut to the chase here by letting this distance, call it R, be the minimum of the distances from P to E sub I, where I'm going to take the minimum over all I from 1 to big N. Everybody happy with that? I'm boxing this because that's the key point. There's a period here, just hard to see. And you should remind the reader why the minimum exists, right? So, and you wouldn't do it by the shorthand I'm doing now. You'd write it out in a sentence, but okay. Exists because the set is finite, right? B, A, E, I are finite. Excellent. And now Katie says, what do you do with that minimum distance? Excellent. And so I would just say then, but the neighborhood of that distance R around P has no points of B. Contradiction. That's a contradiction. Excellent. All right. Any questions about this argument? You could actually have done it not by contradiction if you wanted, right? That's the proof I had written down, but I like this better. Wonderful. Okay. Yes, Harris. She started the proof by taking the negation of what it is you're trying to show, which is there is some neighborhood with only finitely many points. And once you have those finitely many points, you take the minimum distance from P to that point. Yeah, so you could have two things of the same distance, but we don't really care which one we pick. R is still just the minimum, right? Mm-hmm. Oh, and by the way, the other thing you probably have to be a little careful of is this: the negation here. Every neighborhood contains infinitely many points of P. Here you have there exists a neighborhood P with only finitely many points. What if one of the points actually happens to be P? Well, then you just ignore it because you ignore it and look at the minimum that's non-zero, and that neighborhood will not have any other points of E. Okay, so there's something to be a little careful with there. Other questions about this argument? Willie, are you happy with this? Nice, right? It confirms an intuition that you had. Wonderful. Okay, let's define a few more terms. There's a lot of terminology here today, but it's basic for everything that follows. So we have a concept for a set that looks like the nose here. Okay, not geometrically like the nose, but has the property that every point is an interior point. We call such a set open. A set E in a metric space X, I won't write that down, is open means, when I say that if, I just mean means, every point of E is an interior point of E. Okay, so usually when you say interior point, you mean of that set you're in. Okay. So, in that example, you can look at the nose of B is open. Why is it open? Well, every point's an interior point. Basically, an interior point, an open set looks something like this. It's usually some set that doesn't have its, in some sense, doesn't have its boundary, right? It's the kind of picture you should have in your head, right? An open set. Our nose here was like that, right? It's missing a little point, but isn't it true? No matter how close you get to this missing point, there's still a ball around every other point that's completely contained in this set? Yes. Okay. What if the nose had two nostrils? Two missing points. Would it still be open? Yeah? Julian says yes. It would. Okay. It's kind of gross, but yes. It does have, it is open. Okay, excellent. Yes? It could be missing, ooh, that's an interesting question. I mean, there are some configurations in which missing infinitely many points might be bad, right? I mean, I could completely miss everything but a closed set. Sorry, everything, can't use that term yet. So with infinitely many missing points, you'd have to worry a little bit, right? But are there configurations where you could miss an infinitely many points and still be open?
Miss all the points that somehow correspond to rational numbers. Like, if you want to think about it that way.
Yeah, a very interesting question. Can you think of a? I'll let you guys debate and discuss this. Can you miss an infinite number of points and still be open? How many people say yes? How many people say no? Okay, a lot of you are saying yes. So construct an example. Okay, great. Probably most useful would be to know in R, in the real line, what the open sets look like. What do all the open sets look like? I know what one open set looks like. Well, actually, we haven't even said what some of the open sets are. What do they look like? Well, here's a question for you. Is the open ball open? Sure would be nice, otherwise it would be a bad word to use, right? Is the open ball open? More generally, if I take an interval, consider the interval AB, which we normally write with parentheses, which means don't include the endpoints. It's all x such that a is less than x less than b. Is that open? It is? Yes, you're right. And for that reason, we often call this the open interval. Okay. Why is it open? Well, it's certainly true no matter which point you pick, there is a ball around it that's still contained inside this set. Agreed? Okay. That's the open interval. And then what do the other open sets look like? Well, any other open set I claim, we'll see this very soon. If you just take unions of open intervals, you'll get open sets. And those are basically the only kinds of open sets you can have. Ooh, interesting. What about in R? What about the empty set? Is it open? According to our definition. How do people think the empty set is open? How do people think it's not open? Okay, everybody vote. How many people think it's open? More people are convinced of this. Good. Most of you say it's open. Why is it open? It's open if every point of the empty set is an interior point of the empty set. Well, there are no points in the empty set. So this is vacuously true. That's what we say. It's in an empty way very true. It's true that every point is an interior point because there aren't any points. Great. It's open. Good. What about the subset R, the whole real line? Is that open? Yes. Because you clearly can find an interval. Excellent. Okay. We've defined the term open, but we have not defined the term closed. So let's do that. But before I define the term closed, let me caution you, very, very strongly caution you, this is a mistake people often make. A closed set is not the negation of an open set. In other words, because if a set's not open, it doesn't necessarily mean it's closed. Okay, even though even though it's true about doors, it's not true about sets. Okay. Why? Well, let's just see what the definition is. Definition: a set E is closed if E. Okay, now the picture of a closed set is something like this. It's some set that contains, in some sense, all its limit points. That's it. So a set E is closed if E contains all its limit points. Okay. Ah, very good. So closed set kind of looks like something, but the boundary is included in some sense. So let's give an example. In R, let's see if this is true. Is a point closed in the real line? Does it contain all its limit points? What are the limit points of a single point? Nothing. There are no limit points. So it contains all its limit points, yeah? Good. So in R, a single point, P, is closed. The single point P is closed. Okay. What's another thing that's closed? Well, here's another example of something that's closed. This is the interval AB that includes, oh, first of all, is that set closed? AB? Interval, open interval? No. Why? A and B are limit points. So suppose I throw them in. Is this now closed? The claim is yes. So this is the set of all x such that A is less than or equal to x, less than or equal to B, is closed. And that's why we call it a closed interval. Okay. And I will just mention to you that there are the other intervals, A, B, and A, B, where you include either A or B. Are these open sets? Are these closed sets? They are neither open nor closed. Yes? So to be open is not the opposite of being closed. These are sometimes called half open. That's just the way intervals. But the point is, they aren't open, and they aren't, and they're not closed either. Okay, here's another example. What about in R, also in the real line, is the empty set closed? Yes, why? It contains all of its limit points, which are none. There are no limit points. Excellent. Is the entire real line closed in itself? Does it contain all of its limit points? Clearly, they're both closed. So do you see that it's possible for a set also to be both open and closed? The empty set and the whole real line are both open and they're both closed. We have a special name for that. Sometimes people call them clopen sets. Okay. They're clopen. All right. That's kind of, not too many people use that, but it's one of those words that if you say it, people know what you mean, right? It's very clear. Okay. Excellent. So this suggests something, actually, something rather important. This idea that if you have a set that isn't closed, there is a way to try to close it, right? So, for instance, look at this set B, or running example, set B here. Is this set, let's just take a look at this rectangle here, the mouth. Is this mouth closed? Clearly not. It's smiling at you, right? It's not a closed mouth. Okay, but how could I make it closed without shutting its mouth? Oh, maybe I should give it an upper lip. That's right. Yeah, let's give it an upper lip here. And the claim is that's going to be closed. Now, that might seem obvious, but it's maybe not as obvious as it looks. But let's make this definition. So, example, the mouth of B is not closed. Is it open, the mouth of B? Not as a set, right? It's not an open set, right? Okay. It's neither open nor closed. Can we close the mouth? Can we close it? Okay, so here's the idea. The idea is, let's look at, the book uses this term, it's not standard, E prime. Let's let E prime be the set of all limit points of E. will define the term. This is a standard term. The closure of E is defined, well, first of all, it's notated by a bar. You put a bar over the set, that's the closure. It is the set together with its limit points. E prime is not standard notation, E bar is. E prime is just what the book uses. This is very, very standard notation. Okay, that's the closure. And of course, one of the big questions you have to ask yourself is E bar closed? Now, do you see why it's not obvious that E bar is closed? Why is it not obvious? Jenny? Yeah, the issue here is once you throw in this set, to say that E bar is closed means you want to show that the green plus red contains all its limit points. And so you want to make sure that any point that is a limit point of green plus red, that it's maybe possible, perhaps, that that's a limit point of green plus red, but it's not a limit point of green, right? So so there is something to show here, and we will try to show that next time. What do you think the answer is? Yes, because we're calling it the closure. And we'll prove this next time. Okay. Okay, we'll see you next time. Oh, by the way, just one more comment. The notion of a dense set, your book has a definition, but it's much easier if you know what a closed set is. So a set is dense, a set E is dense in X if E closure is all of X. We'll say more about that next time as well.